The Strait of Gibraltar, a breathtaking waterway that separates Europe from Africa, conceals a deadly secret. Beneath its glistening blue waters lies the Azores Gibraltar Transform Fault, the source of historic catastrophes like the 1755 Lisbon earthquake that killed over 50,000 people. Today, we're exploring why engineers haven't been able to cross this narrow gap despite building bridges and tunnels in far more challenging locations around the world. The geological time bomb. Beneath the seemingly peaceful waters where the Mediterranean meets the Atlantic lies one of nature's most volatile geological interfaces. The Azores Gibraltar Transform Fault represents the exact boundary where the African and Eurasian tectonic plates meet in a perpetual, grinding embrace. Unlike convergent boundaries where plates crash together to form mountains, or divergent boundaries where they pull apart, this transform fault creates a sideways sliding motion, generating enormous friction and energy buildup over time. In her research vessel anchored near the middle of the strait, Dr. Elena Vasquez adjusts her glasses as she studies the latest seismic readings from equipment deployed along the seafloor. The monitoring devices send continuous data to her specialized computer systems, painting a troubling picture of what's happening in the depths below. What we're looking at is essentially a geological powder keg, explains Dr. Vasquez, pointing to the colorful visualization on her screen. The Gibraltar Strait sits directly above one of Earth's most dangerous fault zones. This major tectonic boundary is capable of generating catastrophic seismic events. The data streaming onto her monitors reveals subtle but persistent movements, measuring microseismic activity that most people would never notice, but that scientists like Dr. Vasquez monitor with growing concern. She taps a key to display a historical record of the region's seismic activity. November 1st, 1755. The date that forever changed our understanding of this region's seismic potential. On that fateful morning, one of the most destructive earthquakes in recorded history struck the region. With an estimated magnitude between 8.5 and 9.0, the Lisbon earthquake claimed over 50,000 lives and devastated one of Europe's wealthiest cities. The epicenter wasn't under Lisbon itself, but here, in the Atlantic, along this very fault system we're studying today, Dr. Vasquez explains, tracing her finger along the map display. This wasn't a one-time event. It's part of a recurring cycle. The monitoring equipment surrounding her vessel has been gathering crucial data for years, revealing that the fault line continues to move at approximately 4 millimeters per year, a seemingly insignificant figure that masks the enormous pressure building beneath. 4 millimeters might not sound like much, Dr. Vasquez notes, but that consistent movement creates immense strain between the plates. Think of it like slowly stretching a rubber band. Eventually, that energy has to release somewhere. This constant pressure creates what seismologists call a slip deficit, the difference between how much the plates should be moving past each other and how much they're actually moving. That deficit represents stored energy, like a compressed spring gradually tightening. When that spring finally snaps, earthquakes occur. This hidden dance of the plates forces engineers to rethink what is structurally possible. Dr. Vasquez pulls up a graph showing the estimated accumulation of strain since the last major release. Based on our calculations, this fault zone is capable of generating earthquakes of magnitude 8.0 or greater. Any fixed structure spanning this strait would need to withstand forces that most engineers haven't had to consider in other projects. The implications become clear as she displays a simulation of how different bridge designs would respond to such seismic events. Traditional bridge and tunnel designs show alarming stress points and potential failure modes when subjected to the modeled forces. When we design structures in seismically active regions, we typically incorporate flexible components and isolation systems to absorb energy, Dr. Vasquez explains. But the magnitude and specific motion patterns this fault generates create unique engineering challenges. The animation demonstrates how the transform fault doesn't just create shaking motion, but actual displacement of the seafloor. Any fixed structure anchored to opposite sides of the fault would eventually be torn apart as the plates continue their inexorable movement. Beyond the earthquake risk, we have another serious concern for any foundation system: Dr. Vasquez says, pulling up bathymetric charts of the seafloor. The fault zone has created highly unstable substrate conditions. In some areas, we find fractured bedrock. In others, we see thick sediment layers that would amplify seismic waves, a phenomenon known as soil liquefaction. The detailed seafloor mapping reveals a complex patchwork of geological conditions, none ideal for supporting massive infrastructure. Some areas show ancient landslide scars, evidence of underwater slope failures triggered by past seismic events. Other regions display fault splays, secondary cracks branching off from the main fault, creating additional hazard zones. Dr. Vasquez rotates a 3D model showing how these foundation challenges multiply when considering the enormous water depths involved. The engineering solutions that work for bridges in other seismic zones simply don't scale to these conditions. We're combining extreme depth with extreme seismic risk. She pauses, looking out over the water's surface. The placid blue waters belie the dynamic forces at work thousands of feet below. So what happens when you try to build on a geological time bomb? She asks rhetorically. The answer appears on screen as computer models simulate various failure scenarios. In one, support columns snap as fault movement creates lateral displacement. In another, tsunami waves overwhelm protective structures. In a third, soil liquefaction causes foundations to sink unevenly, twisting the entire structure beyond its tolerance limits. These are real concerns, Dr. Vasquez emphasizes. The historical record and our current monitoring both confirm that major seismic events will occur here again. It's not a question of if, but when. What makes the Azores Gibraltar Transform Fault especially dangerous is its capacity for characteristic earthquakes, Dr. Vasquez explains. Rather than releasing pressure through frequent small events, this system accumulates strain over centuries before releasing it in massive, catastrophic ruptures. This pattern means that historical data covering just decades or even a few centuries might not capture the fault's full destructive potential. Engineers designing for a 100-year lifespan might be building directly in the path of a 300-year recurrence event. The stark reality of these findings has forced engineering teams to reconsider conventional approaches. Any viable crossing would require innovative foundation systems that could accommodate not just violent shaking but actual ground displacement, a challenge that pushes beyond the frontiers of current infrastructure design. The